Okay, so we're going to take a look at the problems on this sheet. This is kind of a combination of, it's mostly the stuff we covered just last week. So this is just like extra practice for us. And just going to kind of go through these 5 problems. I'll see how it goes and how much time it takes and all that stuff. Okay, and just let me know if you have questions as we're going along. I can definitely stop and help out. So, everybody good to go? Mm-hmm. Okay, great. So the first problem here is actually about accumulation points again. So maybe I should remind you what that means. So X, so this is just a definition, just to remind you. X is an accumulation point of A, which is a set. So A is a subset of R. And X is just any real number. So X is a real number, right? For all epsilon greater than 0, so for every neighborhood of X has to intersect with the set capital A minus X. So for all epsilon greater than 0, U sub epsilon of X intersects with A minus X. Okay, so if you look at, and of course, if X is not in A, well then you're not really subtracting anything, you're just looking at A itself. But if X is in A, then you take it out of A before you compare it with the neighborhood, right? And so X is a real number, it may or may not be in the set A. Okay, so we know that. You know, the best example of accumulation points to try to understand what they're talking about is the sequence 1 over n. This is going to be the one that you want to use as your prototypical example. You have all of these dots here coming towards 0, and 0 itself is an accumulation point, even though it's not in the set. Because every neighborhood of 0 has to intersect some of the elements of capital A. Capital A is just the dots that you see here. This is the set capital A. So it's kind of weird. The only accumulation point of this set happens to be a point that's not in the set. But, you know, that can happen. That can happen. Okay, so that's the definition. So with that in mind, we're going to prove on number 1 the following thing. So prove that X is an accumulation point of A if and only if every neighborhood of X contains infinitely many points of capital A. Okay? So we're going to prove this is an if and only if. So kind of makes sense if you look at this example. Every neighborhood of 0 contains infinitely many terms of the sequence 1 over n. Right? So this is the sequence 1 over n here. Okay? So I think that seems reasonable. Does everybody feel like it should be true? Okay. So if you take an accumulation point, you draw a neighborhood around it, it should have infinitely many points of A in that neighborhood. Right? Okay. So I have to prove this both directions. Does anybody care which way we prove this first, or doesn't really matter to me? Do you guys want to think about using the definition to prove this, or do you want to start with assuming every neighborhood contains infinitely many points and prove that this is true? This way? Mm-hmm. Is that because you think this is easier, or because you think it's harder?
Well, the definition's already up there, so.
Okay, so we already have the definition up here. Okay, well, let's prove the forward direction. May as well. Turns out the forward direction is the hard part.
No, wow.
That's okay. Hey, we have to do all the work anyway, so we may as well get the hard part done first. Okay. So we're going to assume that X is an accumulation point. So I guess I'll write that down. Assume X is an accumulation point of A, and then we need to show that every neighborhood of X contains infinitely many points of A. So I'm going to take an arbitrary neighborhood of X and show that it has infinitely many points of capital A in it. Okay, so let And every neighborhood is indexed by an epsilon, right? So I'm just going to say, let epsilon greater than 0 be given. And consider, right, it's the usual way we write this up, consider this neighborhood around x a radius epsilon. Okay, so far so good. We have to show that that neighborhood contains infinitely many points of A. And we know that that neighborhood, oh, I forgot to say here, this intersection is non-empty. That's what I'm supposed to say. Didn't quite finish that statement, did I? Every neighborhood non-trivially intersects with A minus x. That should have been up there. Okay, so we know that this neighborhood, when we intersect it with A minus x, there's something in there. Okay. Any ideas how we're going to prove that U sub epsilon of x contains infinitely many points of capital A?
Do we have to show that it's like there's a projection to an infinite set? Or no, is that too much?
I think that's getting too much wrapped up in the definitions from chapter 2. You know, I think showing it twiddles n or something, that's going to be a little bit more than we want to deal with.
To do it by way of contradiction, if you assume finite?
Exactly. I would do this by way of contradiction. So the idea would be this. Let's just kind of get the intuition behind that strategy. Okay, so here's our point x, and here's our neighborhood around x. The idea is if there are if there were finitely many points of A in this neighborhood, right? So maybe here and here. So I'm doing open circles on the points of A. So if there were finitely many of them, then you see that this x is kind of by itself a little bit. So you see that what I would be able to do would be to make a smaller neighborhood here, which has no elements of capital A in it, and that would violate this definition. See, we're assuming that x is an accumulation point. That's the intuition behind it. Okay? Can we try to, let's see if we can write this up then. Okay, try to write it up. Okay, so by way of contradiction, it's always good to just have the picture, get a little intuition first, then we can go ahead and try and proceed from there. Here's a handout here. So by way of contradiction, let's suppose that U sub epsilon of x has finitely many points of capital A. Let's give them names. Let's say A1, A2, up to A sub n. So those are finitely many distinct points. Okay? Now, what we could do is maybe, so one of these points could be x, right? Because x could be in A, in which case that neighborhood, this x is really also open. It's one of the elements of capital A there. So let's just maybe break that into two possibilities. Let's say, let's suppose that x is not in A, right? Then, so in other words, x is not one of these points, this finitely many points. Then how am I going to find this epsilon that's like creating that dotted neighborhood? Like how is that radius determined?
The minimum distance between x and A.
Right. We basically take the minimums of the distance from x to each of those open circles, and whichever one is the smallest tells you which one is the closest to x, right? So that's exactly what I would do. So I would set, let's call it epsilon prime, to be the minimum of the absolute value of x minus a1, comma x minus a2, comma dot dot dot, comma x minus an. Okay. Now the point is that none of these differences is 0 because x is not in A right now, right? And all of the A1, A2, and A3, and so on, those are in A. So that means that these points are distinct from each other. X is not in A. I'm making a case right here. I'm I'm making a case 1 or whatever. If x is not an A, then we just do this. Does that make sense? Okay, then the point then is that this is strictly positive because all of these absolute differences are non-zero, right? Making sense? So that's how you get the radius that you want. Okay, so then the point is, then if I look at u sub epsilon prime of x, right, the neighborhood, which is that dotted neighborhood, if I intersect that with, I'm going back now, I'm going to contradict the definition, right? We contradicted this side, we're doing by way of contradiction. The negation of this side has to lead us to the negation of this side. X should not be an accumulation point of A, which means there should be a bad epsilon that makes this condition not work, right? So my bad epsilon here is going to be epsilon prime. So I'm going to take this, I'm going to take A minus x here. Okay, in this case, x is not in A, so we're really just, so basically this is just, it's just A, exactly. This is just intersecting with A. You don't have to subtract x from A because it's not there in the first place. Okay, and what we've done is we've actually excluded all of these open circles that were the elements of A. In other words, this is empty. This is empty, and that is a contradiction. Does that make some sense? Right, so we found an epsilon. Now this epsilon is not the same as the epsilon we started with. Okay, because there's an epsilon here for the neighborhood of x that we're looking at, and then there's also an epsilon on this side of the biconditional for the accumulation point, and they're not necessarily the same number. Okay, what do you think I should do in the case when x, let's say x is an element of A, in which case it would maybe be one of these elements A1 through AN. What do you suppose I would do in this case?
Just exclude those ones.
You don't want to take the minimum of all these distances again because one of them would be 0 and then your epsilon prime would be 0. But what you can do is just exclude that one. Just exclude A1. So in other words, in this case, you just set epsilon prime equal to the minimum of x minus A2 dot 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 up to x minus AN, like that. And this again will be greater than 0, and then I'm just going to say proceed as before. In other words, just repeat the other case again. You guys believing that? This is the hard direction of the proof. The other part is going to be a lot easier. Okay. Yeah, go ahead.
So that intersection is empty because we excluded all of the points that could possibly be around x.
Right. We've excluded all of this. These are all of the elements of capital A.
Okay.
Right? So, and there are only finitely many.
Right.
If you had infinitely many elements of capital A there, you would have a minimum of an infinite list. A minimum of an infinite list of positive numbers could still be 0. Because one of those positive numbers could be 1, and the next one might be 1/2, and the next one might be 1/3, and the next one might be 1/4. If you take them an infinite minimum, which is really taking an infimum, right, you would actually get 0. So your epsilon prime would be 0, which wouldn't be allowed. I'm making a big point here that this epsilon prime needs to be positive to make this make sense.
So that's basically the way that we construct those little dotted interval.
Correct.
Okay.
Yeah, this radius here is epsilon prime
Okay.
on both sides. Exactly. And the big radius was the epsilon. Like that. Yeah, exactly. Okay, does that make sense? Okay, perfect. Now the other half of this is a lot easier. Okay. So for the backwards direction, I'm not gonna write down the assumption because it's just gonna take, I'm just gonna rewrite everything that's already up there. I'm just gonna say we need to show x is an accumulation point of A, and what we are given is that every neighborhood of x contains infinitely many points of A. Okay, so let's see, what do we have to do? We have to prove this accumulation point property, we have to show that every epsilon gives us this condition. So let's let epsilon greater than 0 be given. Okay, whenever you're proving for all epsilon something is true, you just have to start with an arbitrary epsilon and go from there. So every epsilon greater than 0, we're going to prove that it has a non-trivial intersection with A minus x. Okay? But what we know, what we are given, is that every neighborhood of X contains infinitely many points of A. So, starting from epsilon greater than 0 be given, can we make a neighborhood? Because we know that every neighborhood of X has some property. So the question is, well, how do we get a neighborhood? Well, every time we have an epsilon in our hands, we can make a neighborhood to which we can apply this assumption. So that would be, I don't even know if this is going to work yet, but that would be the only thing I would know what to do. It's like, gee, I've got to use the assumption. It means I need to have a neighborhood of X in my hands. How can I get one in my hands? Well, if this is all I have on my proof so far, that's just the epsilon that's going to be the radius of one of those neighborhoods, right? So I would just say, consider the neighborhood u sub epsilon of X, right? Okay. By assumption, it contains infinitely many points of capital A. By assumption, it contains infinitely many points of capital A, right? And this is what we're trying to prove up here, is that this neighborhood has a non-trivial intersection with, basically with A. But look what we know, that this neighborhood contains infinitely many points of A.
So it has to be non-trivial.
So yeah, this intersection has to be non-empty, even if X is in A, right? There's still, if you take, so infinitely many points of A, X could be one of those points, but there are still infinitely many others that would still belong to this difference and make this intersection non-empty. That's really the point. Okay, so then I'm just going to say, thus, it is clear, famous last words, right? It is clear that u sub epsilon of X intersected with A minus X, which could be A or it could be 1 point less than all of A. Either way, this is an infinite set. This is an infinite set of elements that are in this neighborhood, right? So if it's infinite, it's definitely not empty. If it's infinite, it's definitely not empty. So that's the proof of the backwards direction. A little bit more straightforward. Does this make sense? Mm-hmm. It's a nice little example to practice what it means from the definition for something to be an accumulation point. Okay, in class we did some examples of sets and we looked at what are the accumulation points, and we got some homework on constructing some sets that have accumulation points of certain types. But this is actually a more theoretical proof. And this is useful for you to think about in the future, because now if you don't like the definition of accumulation point up here, let's say you don't like that definition, you never have to use it again, you can just use this. Okay? If I want to prove that X is an accumulation point, I just have to show that every neighborhood of it contains infinitely many points of the set. That could be a useful way of thinking about what an accumulation point is. It's a little different than the definition. Good enough? Okay, great. So that's the first problem. Let's go on to the next one. The next one is another chance to practice limits at infinity. So we'll do that here. You had one problem in the group work where you were kind of looking at this concept. I didn't really lecture on it in class. It's kind of a quick little thing. So number 2 says, show that the limit as n goes to infinity of n minus 6 square root of n is equal to infinity. In other words, if you think of this as x sub n, you're just really showing that it converges to infinity. So this converges to infinity. It's basically what you're proving. Okay. So let's start this problem off by also remembering the definition, because it was only in that group work and it may not be on the tip of your tongue right now. So let's just write down what this means to say that a sequence converges to infinity. Okay, so the sequence converges to infinity. This is something hopefully you could kind of come up with the definition even if you've forgotten it. I mean, I hope you don't forget it. It's good to put it on a flashcard. But it basically just means that, okay, so here's my number line, that plus infinity is over here. The sequence is converging to infinity really just means that the terms go arbitrarily far to the right, which really just means that if I give you any alpha value, I think I called it alpha in the definition, the sequence eventually passes to the right of alpha and stays to the right of alpha forever. It's kind of what it should mean, right? That's what it should mean. So what this is, the way I'm going to phrase this here is that, well, for all alpha greater than 0, and if you used an epsilon instead because you didn't remember what the notation was, that would be fine. I think they just don't want to use epsilon because that's already so attached to the idea of convergence to a real number. So they just want to give you a different symbol to help distinguish this a little bit. So for all alpha greater than 0, there exists an n naught in the natural numbers such that if n is greater than or equal to n naught, right, then, well, the absolute value, actually you don't even really need absolute values here because you're really just saying the terms themselves are getting arbitrarily far to the right. So n minus 6 radical n, right? And we're not going to subtract something and set it less than epsilon anymore. We're simply going to say this should be greater than alpha, right? That's basically what we would expect to say. Okay. Everybody good with that? Does that make some sense? Okay, so we kind of need to try and solve this for n. In other words, that would be probably the best way to proceed. So, just as we do with our epsilon n naught proofs, some scratch work, kind of thinking backwards about it would be maybe a good idea. So we do some scratch. Let's see, n minus 6 radical n greater than alpha, if and only if. Does anybody have a suggestion how I could kind of solve this somehow or get n?
I move the alpha over and use it might not be the easiest way. I move the alpha over and use the quadratic equation, but I think we don't need that now that I see it, because then when you want positive ends only. So.
Okay, so what are you suggesting exactly?
So square both sides, sorry.
Square both sides. Okay, let's try to square both sides. So that I understand.
Well, initially, like what I wrote.
Yeah, no, I understand. It's not always perfectly polished the first time you do it. Okay, so we square both sides. So what do we get here? We get n squared minus 12 times n to the 3/2 power, I believe, and then plus 6n is greater than alpha squared. Is that what you were thinking? Well,
yeah, that's it.
Yeah, so that, oh actually, sorry, 36 here.
Yeah.
36. This should be 36n. Okay.
The quadratic is probably the easier way now.
So this is not really a quadratic polynomial though, right?
No, right? Like quadratic from the beginning.
Maybe what we could do, I have another idea. How about we actually solve this for a radical n and then square both sides? Might be a little easier. Okay, so if I move the n minus alpha over and just say, greater than 6 radical n, right? Try that. If I now square both sides of that one, I'll have n squared minus 2 alpha n greater than 36n. Oh, there's plus an alpha squared on that, sorry. Plus alpha squared greater than 36n. Okay, now I see how I can write this as a quadratic, right? Because I have n squared, come over here a little bit, n squared, and then how many n's do I have? Well, it's going to end up being 2 alpha plus 36 times n, I think. Right? So I'm going to combine these two terms because they both have an n on them, and then plus alpha squared greater than 0. And now I have a quadratic formula in terms of n squared with an n coefficient and a constant coefficient. So now we can try to use the quadratic formula. I know, it looks a little ugly, but that's not going to be that bad. So this gives us, so solving n is equal to the negative of the b coefficient in the ax squared plus bx plus c formula. So the negative of this would just be 2 alpha plus 36. Okay, plus or minus the square root of 2 alpha plus 36 squared minus 4 alpha squared all over 2. Okay. That's the values of n that make this equal to 0. So technically we will want to choose n's that are larger than that. Right? N's that are larger than that. Okay, so you could just sort of stop there. Let's simplify it though a little bit. So if I simplify it, n is greater than 2 alpha over 2 is just alpha. 36 over 2 is 18. And then so alpha plus 18 plus or minus. When I look at this, I'm going to put the over 2 back in there. When I square this out, notice you'll get a 4 alpha squared, which cancels the minus 4 alpha squared. And then the cross term is going to be 144 alpha, and then 36 squared is, what is 36 squared? I don't know.
1,296.
No, it's a big number. 36 times 36.
1,296.
1,296. Yeah. There we go. Okay. So that would be what it would be equal to. Okay. So yeah, you could just simply. This is clearly not going to be negative under here, right? So because alpha is greater than 0. So just basically choose n naught in the natural numbers with n naught greater than alpha plus 18. Let's just use the plus value here, not the minus one. Let's pick the largest of the two roots so that we are sure that everything above that value will work. So all of those values, right?
So this is now like back in the proof.
Yeah, now we're back in the proof. So choose n naught that way. Okay, and then you just got to trace the steps from there. So the hard part of it is just solving for the n, really. But the concept of it isn't so bad. Okay, so then I'm just going to say from there we can just retrace these steps. Okay, so now retrace the scratch to finish the proof. So in other words, if you started here and you said let n naught be greater than this, then if n is greater than or equal to n naught, then n will be greater than this, right? And if n is greater than that, then n is greater than this, right? And therefore, this will be true, because this is just a parabola, right? So if n is greater than the larger of the two roots, right? It's greater than both roots, but in particular it's greater than the larger of the two roots. So if you have a parabola with two roots, right? N is over here somewhere, right? So as long as n is over there, then when you plug that n into the parabola, it's going to be greater than 0. So you're up here, if you plug any n in from over here, it's greater than 0. So therefore, now the rest of it is just this algebra. Yeah. So, everybody okay with that? Makes some sense? That's a nice little problem. It's just a little tedious, but not really too bad. Okay, perfect. I see. Okay, perfect. Okay, let's go on to another example. Number 3 here. This is the last one about sequences, I see. Okay, so on this one, let x1 equal 1, and then let xn plus 1 equal 1/4 of 2xn plus 3. And then it's just going to say, show that xn converges. And find the limit. Okay. So that's the question.